Unit 8, Lesson 9, Multi-Step Experiments. I can use the sample space to calculate the probability of an event in a multi-step experiment. So we're going to look at the probabilities of experiments that have multiple steps. So spinning a color and a number. So what do you notice and what do you wonder? Okay, so what do I notice? I notice there are 4 colors and 5 numbers. Each section is equal. What do I wonder? How many times they're going to spin the spinners? Okay, you could wonder things like, what's the probability of getting a certain number? You could wonder all sorts of different things about this. All right, so they want us to remember, for sample spaces where the outcomes are equally likely, the probability of an event can be computed by counting up the number of outcomes and then dividing it by the total number of outcomes. So the desired outcomes divided by the total number of outcomes in the sample space. So for example, if we wanted to get the probability of heads and rolling an even number, there are 3 ways to do this out of 12. So if you look at it, there's a heads and a 2, a heads and a 4, and a heads and a 6. So that's 3 that meet the criteria of heads and an even number out of 12 possibilities, because if I counted that up, I would get 12. I can reduce my probability to 1/4, which means that I can divide the numerator and denominator by 3 and get 1/4, or I can do 1 divided by 4 and get a 0.25 or 25% chance. All right, so how many outcomes are possible? So if you remember when we did this before, there are 4 possible outcomes on the first spinner, 5 possible outcomes on the second, and we're going to multiply those to figure out all the total outcomes. So that's going to be 20 outcomes. I could also draw a T-chart where I go red, blue, white, green, and then I count off 1, 2, 3, 4, 5 for each one, and then when I counted all those up, I would get 20. Either strategy works. So what is the probability of getting the following outcome? A red and a 1 or 5. So a red would be a 1 out of 4, and then a 1 or a 5 would be 2 out of 5. So I'm going to multiply these. So 1 times 2 is 2, 4 times 5 is 20. So 2 out of 20 would also reduce to 1/10, which could also be 0.1 or equal to 10%. So all of these are equivalent. They're all equal to each other. They're just in different forms: fractions, decimals, and percents. So what's the probability of getting a green and a 3? So that's 1 out of 4 and a 3, so that's 1 out of 5. So that would be 1 out of 20. Or I could draw it out and count them up. What is the probability of getting a blue and any odd number? So a blue, so that's 1 out of 4, and an odd number, so that's 1, 3, and 5. So that's times 3/5. So that's 3 out of 20. All right, drag your dot to indicate your understanding. So if you're in Pear Deck right now and you're doing it, you're going to take this dot and you're going to drag it where you think you fit on this. What is the probability of getting the following outcome? Any color other than red. So that would be 1, 2, 3, so 3/4, times any number other than 2. So that's 1, 2, 3, 4. So that would be 12 out of 20, which reduces to 6 over 10, or 3 over 5, which could also be 6/10, which could also be 60%. So, so any of those, these are all equivalent, and you have to be able to recognize equivalent percents, decimals, fractions. All right, so the next one's cubes and coins. All right, you do a chance experiment where you roll a number cube and flip a coin. Write out the sample space in any organized strategy. So I roll a number cube and flip a coin. So I'm going to choose a tree diagram. So that's 1, 2, 3, 4, 5, 6. And then the next would be a heads or tails. Now I could write this out as a table. I could write this out as a graph or as a organized list, or a tree diagram like I'm doing. So what is the probability of getting tails and a 6? So tails and a 6. So 6 and a tails. So that would be 1 out of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 options. Or I could have figured that out by going 1 out of 6 times 1 over 2, which would also give me 1/12. All right, the next one. Which makes the most sense to you? So which strategy at this point makes the most sense to you? Now, we've done this activity before. So in this case, the strategy that makes the most sense to me would be this one. But you've seen me do this one a lot, and I can do this one now. I feel more confident with it than I did a couple of lessons ago. So you have to decide which one makes the most sense to you. All right, so suppose you roll 2 number cubes. What is the probability of getting both cubes showing the same number? Okay, so I put in a graphic here of a T-chart, or I'm sorry, a tree diagram that shows this. So both cubes showing the same number. So that would be, let me change colors. So it's 2, 3, 4, 5, 6. So it would be 6 out of, and then 6 groups of 6 would be 36, or 1/6, either of those probabilities. Exactly 1 cube showing an even number. Ooh, okay, 1 cube showing an even number. So there's half of the cubes options are even, or I could rewrite it as 3/6 are even numbers, and exactly 1 cube is showing an even number, which means that the other cube would have to show an odd number. So that would be times 3/6. So these would be the evens, and these would be the odds. So that would be 9 out of 36, which could be 1/4. At least 1 cube showing an even number. So 1 cube has to show an even number. So, why don't we go back to our tree diagram and look at it there? At least 1, which means it could be both. So keep that in mind. It could be both. So that 2, 3, and then all of these would work. So that's 9 because that's at least 1. And then all of these because 4 is an even number. And then all of these because 6 is an even number. So that's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So 27 out of 36. So let's think about what that could be. So 3/4. So if I wanted to think about a scenario where it would work every time, that's how I could do it. Two values that have a sum of 8. So you roll 2 cubes and they have a sum of 8. Okay, so let's go back. So that could be 6 and 1 add up to 7, so that's not going to work. But 6 and 2 add up to 8. 3 and 5 add up to 8. 4 and 4 add up to 8. 5 and 3 add up to 8. But 6 doesn't add up to 8. So that's 4 out of 36. Or 1/9. And the last one is two values that have a sum of 13. All right, let's try again. So see how the T diagram is really helpful in this situation? Sometimes multiplying the fractions work, and sometimes it's easier just to draw out your T diagram and draw it in. So 13 is what I'm looking for. So 6 plus 7 is 13. 5 plus 8 is 13. 4 plus 9 is 13. So that's impossible. So that would be 0 out of 36. Because the largest you could get would be 12, 6 plus 6. So the probability is 0 out of 36. All right, Jada flips 3/4. What is the probability that all three will land showing the same side? Okay, well, let's draw it out. Heads, tails, and then you could have a heads or a tails. And then the third coin, heads, tails, heads, tails, heads, tails, heads, tails. So that's 1, 2. So 2 out of 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes, or 1 in 4. So there's a 1/4 chance that all of them, or 0.25, or 25%, all of them are equivalent. All right, did you have a method for finding the number of outcomes in a sample space or an event that was more efficient than just counting them? Yes, multiplying all the possible outcomes. In each event. All right, so now let's take a look at our cooldown. So Lynn plays a game that involves a standard number cube and a deck of 10 cards numbered 1 through 10. If both the cube and the card have the exact same number, Lynn gets another turn. Otherwise, play continues with the next player. What is the what is the number of possible outcomes, and what is the probability that Lynn will get another turn? So you could draw out a tree diagram, you could draw out a table, you could do a list, you could use your multiplication factors. So then I need you to go ahead and submit this, and I hope you have a great rest of your day.